Okay, now I want to introduce to you how to do hypothesis testing on correlation. So here's the data of 6 countries where they list the amount of chocolate consumption in kilograms per person times year versus the number of Nobel laureates per million. So looking at this, which one do you think it's United States?
10.
It's either this one or that one, right?
Yeah.
Maybe Great Britain used to have a lot of Nobel laureates, so maybe one of them should be England and one of them should be United States. Okay, but anyways, so suppose you have such a data point, okay, and you want to check this hypothesis. Okay. So, how do you do that? Well, what it really does is, let's start with step 1. So step 1. In any hypothesis testing, what is step 1?
State your claims.
Yeah, you have to state your hypothesis, right? So the null hypothesis here is that correlation coefficient of the population is 0. So, we go by this convention that Roman letters mean values of the sample, and Greek letters are they denote the values from the population, which often is not accessible. So we don't know the true value of rho. We only have the R value computed from the sample. But the hypothesis is that there is actually no correlation between chocolate consumption and number of Nobel laureates. Okay? So that's your null hypothesis. And then the alternate hypothesis is that, well, there is some correlation. So that's alternate. And for hypothesis testing of correlation, we don't have, you could make something up, but usually you don't do one-sided, one-tailed test. It's always two-tailed. Okay? It's either there is no correlation or there exists some correlation. That's going to be the, there exists some kind of correlation. That's the alternative hypothesis. Okay, and then you would, in step 2, you would think about the rejection region, right? Now, there is, when you talk about the rejection region, you have 2 options. There's one way to use the T distribution, t-test, where I don't know who, I think it was Pearson that first proved this. He proved that if you let t equals to the correlation coefficient r computed from the sample, divided by square root of 1 minus r squared over n minus 2, with degrees of freedom, t distribution always requires degrees of freedom, right? And degrees of freedom n minus 2. Now the reason that you have n minus 2 as the degrees of freedom is because for a line to be determined, you need 2 points, right? So somehow if you have n data points, 2 of the data points is already used up to figure out the line in some sense. So out of the n, about 2 of the information is used to figure out B0 and B1, okay? And then the remaining is somewhat used to figure out what R is. So that's why we say that the degrees of freedom is n minus 2. Well, someone proved that this transformation makes can convert the value of the correlation into something that follows a t distribution, and did this. Yeah, I can. Yeah, it's hard for me to see where that formula comes from. Yeah. So you don't have to know. Okay, so that's one way to do it. Okay? But rather than using this in this class, we'll just use the row test. Okay. So what we do is there's the row table of row values. So I handed out this Pearson row table, and according to the row table, and again, let's just say that this is 0.05, significance level is 0.05. So if you go to significance level 0.05, what's our degrees of freedom?
2.
Well, there's 6 data points, right?
Oh yeah, 6.
Minus what?
2.
2. For linear regression, you have to subtract 2. And that gives you 4 degrees of freedom. So we look at the table,
0.7.
yeah. So that gives you
0.
row critical is 0.8114.
811.
0.8.
Right?
Yeah.
8114. Okay. So that's the critical. So there are 2 ways. There is this way to do it, but we will not be using it. But if you ask, how did somebody make this Pearson row table? They made it by doing this conversion. Okay, so internally, this is what's going on, okay? Which we don't care. We'll just be using the row. Okay? All right. So then what we do is now we have to calculate the regression. Oh, okay. So you have to help me out here. So to get you have to calculate the test statistic, your R from this. You have to use your calculator to figure out the R value. So the way you do calculate R by calculator is what you do is go to stat. So if you have a calculator, please try this. Stat, and then you go to edit. And there you can start editing the values of L1 and L2. So you have L1 and L2, and you start plugging those numbers in. So you have 4.5 and 5.5, 10.2. Well, you just keep putting in L1, right? So 4.5, 10.2, 4.4, 6.3, 2.0, 8.5. You punch this in, and you go to the next one. The second L2, you put in 5.5, 24.3, 8.6, 9.0, 1.9, and 25.3. You put all this, and now you exit, okay? After doing the exit, again go to stat, go to tests, and you're going to pick linear regression t-test. Okay. It's called t-test because of the existence of this transformation, but what it really does is it just calculates everything for you. It gives you many different things. It will tell you y equals to a plus bx. So it'll tell you the y-intercept and the slope of the regression line. It will also give you the value of r, okay? And plus other things as well. Okay. All right. So can you tell me what a plus a is and what b is? Did anyone get it?
A is negative 6.221.
Okay. Plus b is
3.12.
okay. So you have negative 6.22 and then 3.12x. Okay. What's the value of r?
0.8. 941.
Okay. And now, step 4. What's your conclusion? This is?
In the rejection.
Yes. So this has too much of a high correlation to say that there is no correlation. It's like very close to 1, right? So since this is in the rejection region, we reject H0 and say that yes, there is a correlation. Okay? Between chocolate consumption and number of Nobel laureates. Okay? Okay, so that's how you do hypothesis testing of correlation between two things. But there's more. Okay, it doesn't end there. There are a few follow-up questions that you have to answer. But let's wait and let's stop here and think for a moment. One would look at this data and say, wow, really? So in order to have more Nobel laureates, it's not that we should pour more money on STEM education. We should just make more chocolate and make, like, the government should be funding the chocolate so that kids can eat more and more chocolate. That's going to help us have more Nobel laureates.
No.
Is that right?
No.
No. What's the problem with that thinking?
Correlation is not equal causation.
That's very good. Yeah, correlation is not causation. Okay? It's a very important thing that every engineer, every scientist, anyone doing and working in the STEM major should know, that even if you observe some kind of a correlation between two variables, it doesn't mean that one is a cause of the other. Okay? Rather, it's more convoluted. Like richer countries will have kids asking for more sweet things, and their parents are going to buy more sweet things, because all the corporates in those countries are corrupted, and they, you know the story, right? Okay, so that's why they're going to have huge amount of chocolate consumption. But because they're also rich, they can also fund more research, thereby allowing more people to have the Nobel Prize, right? So that's probably what's going on here, rather than the chocolate consumption immediately affecting the Nobel Prize. Okay, and another thing is you should also sometimes like have some doubts about your data if something so unrelated has some kind of correlation. Maybe what happened was that the countries that you're sampling from were mostly from European countries. Okay? And then now you start including Japan, for example. They don't eat much chocolate, right? But they do have a lot of Nobel laureates, right? And then once you put that extra column in, then you'll see that, well, I can't show you I can't recall the actual values, but I remember that if you put that in here, then suddenly the correlation gets destroyed because this has such a low degrees of freedom. Suddenly it gets destroyed and you don't see that correlation anymore. So sometimes poor sampling can give you a false sense of correlation between two things. Okay, so that's another thing. All right. So so that's how you do the hypothesis testing, but there usually will be some follow-up questions to hypothesis testing. So the next question, this could be like the hypothesis testing could be question part A. Part B would be something like estimate the number of Nobel laureates per million if chocolate consumption is equal to, say, 5.2. So let's say you looked at a country and that country had chocolate consumption of 5.2 kilograms per person per year. What do you think is the number of Nobel laureates in that country per million? Well, how do you do it?
Plug into the equation.
To this linear, see, this is your linear regression, right?
Yeah.
And we use this and we put 5.2 and whatever that value is the value. So can you, so the answer is y is equal to negative 6.22 plus 3.12 times 5.2. Okay. So what do you get?
10.
You get 10?
Yeah, 10.004.
Oh, okay, 10. So you get 10. Okay? Now, what justifies us to use that regression line? Can we always use the regression to come up with a prediction?
No.
Why not? That's because we can use it because our hypothesis testing came out significant. So when the hypothesis testing comes out significant, that means this has some predictory power. So that means that allows us to use 10. However, if this value from the sample, the correlation coefficient from the sample wasn't as big as the querical row, and we couldn't reject the null, if that happens, then we shouldn't be using that. Instead, what do you use? You use the average value of the Nobel Prize. That's what you use. So that's another important thing. Okay? If the test was not significant, y bar should be the prediction. Because average value is the best predictor if you have no way to judge what the ideal number would be. Okay? So that's another important thing. So when you're solving a quiz problem or an exam problem, when you're being asked to estimate something, and the first part was a hypothesis testing, then depending on the outcome of that, if it comes out significant, use the regression equation. If it doesn't come out significant, then you just use the average one. Yes?
So if it comes out significant, no matter what value you give us for that question, we still use the average?
That's... well, that's a bit... Okay, yeah, that's a really sharp question. The thing is, see, there's... Usually when you have a linear regression, a lot of times it actually happens more when you're using this for machines, stuff like that. It has a range where it's very linear, and then beyond something or below something, it fails to be linear anymore, and then you get some very different value. And that's another, in practical usage, that's another problem. If you had a country where the chocolate consumption was 20, it's like way out of the range of what you're used to see. So in that case, it might not be wise to use that. Yeah. But I wouldn't put that.
Okay.
Yeah. For the exam purposes, that's not a problem. But in practical use cases, there is a danger trying to use this for any input value. Because if it's too large or too small, it might be outside the range that's linear. Very good question. All right. And then part C, let me see if you understood enough to answer part C. Part C would be asking what percent of the variation in the number of Nobel laureates in million is explained by the regression. Okay. How would you answer this? What percent of the variation in the which value describes such a thing? If you want to know what proportion of the variation of the y is described by y hat,
Capital R.
the capital R
Squared.
squared. Right, so the answer should be capital R squared, which is this value 0.941 squared. Okay, can somebody do this? 0.885.
885.
Okay. So that means that 88.5% of the Nobel laureates' variation is explained by the linear regression, which means it has a lot of explanatory power. Okay. Okay.